Hello and welcome to this clip looking at using a pH curve to work out pKa values of the various species into which a triprotic acid can dissociate. So let's have a think about what a polyprotic or multiprotic acid might mean. So these are acids that contain more than one acidic proton, such as sulfuric or phosphoric acid, which you've come across before. The protons aren't released at the same time, and usually what happens is the ones released first involve a stronger dissociation than the ones released afterwards. And this process can be recorded during a titration curve. Each successive dissociation will involve an acidic species created in the preceding one, so the reactions happen in a specific sequence. And each acidic species will be negatively charged, apart from the first one, of course, because it will have lost a positive proton, meaning it's negative by default. So each acidic species will be a conjugate base that was previously produced. So therefore, because it's negatively charged, it'll be harder to release a proton again, because there'll be an attraction between the proton and the acidic species. So if we look at sulfuric acid, the first dissociation will involve a proton being taken from a neutral molecule, your H2SO4. So this isn't too difficult because there won't be a particular attraction between H+ and H2SO4. So this dissociation is where sulfuric acid behaves as a strong acid. But look what happens to the HSO4. It still has a hydrogen atom within it. So you can actually remove this hydrogen as well as a proton. So in other words, the H in HSO4 can come off as a second dissociated proton. But what's happening here is you're taking away a positively charged proton from an already negative species, HSO4-. This is clearly harder because there will be attraction between them. Therefore, the hydrogen sulfate ion will behave as a weak acid. So looking at citric acid very quickly as well, this has 3 separate carboxylic acid groups. So 3 weak acid dissociations, with each one being weaker than the previous one. So let's look at an example of a polyprotic acid's titration curve. So phosphoric acid dissociates in 3 stages if it's titrated with a strong base such as sodium hydroxide. You can see the sequential reactions on the right-hand side. So going back to equivalence points in titration curves, you can see it's got 3. And in the diagram, it's got each half equivalence point being written out as a midpoint. And those midpoints, half of the acid species that's being neutralized has been used up. So at this point, or each of those 3 points, the acid species that's reacting, the concentration of the acid is equal to the concentration of the conjugate base. And this means that pKa equals pH. So looking at the first one, I've changed all the species on the right-hand side that are acidic into red so you can follow it. We're looking at H3PO4 to start with. So at this half equivalence point, pH equals pKa, and therefore the Ka for phosphoric acid at this point will be calculated by doing 10 to the minus pKa. So 10 to the minus 2.16 will give us 6.918 times 10 to the minus 3 moles per decimeter cubed. Going on to the second species, we now have the H2PO4- that was made in the first dissociation, undergoing a further dissociation. This is the second dissociation now. Another hydrogen comes off. Again, at this point, pH equals pKa. Using the same technique, you can calculate that the Ka value for H2PO4- is 6.166 times 10 to the minus 8 moles per decimeter cubed. Finally, moving on to the third midpoint, the third half equivalence. This involves the HPO42- that was made in the second dissociation, releasing its proton, This is the third and final proton coming off of H3PO4, leaving behind phosphate ion. So once more, you've got pH equals pKa. So therefore, the Ka for this species, HPO42-, is 12 to the minus 12.32, which gives us 4.786 times 10 to the minus 13. This means that the lower the pKa value, the weaker the acid. And the conclusions we can make are that the half equivalence point can be used to prove that pH equals pKa at the point where half neutralization has occurred. The pKa value gets lower with each successive dissociation of an acid with more than one acidic hydrogen. And this can be proven via the use of a titration curve like this. Okay, so hopefully this has been a useful extension into titration curves, an introduction to how polyprotic acids work. And until next time, thanks for listening and see you soon.